In this section, we're actually going to be connecting the scatter plots that you did in 9.1 with a bit of algebra. We're going to take it back to what you were doing with equations of a line, looking at slope of a line. Remember that positive slopes go up and to the right, and negative slopes go down and to the right. So we're going to take a look at how that can be used as a tool for estimating where additional data points might fall within the field. There are two key words for you up here. The first is most. We're looking for lines from which most points in a scatter plot are within roughly the same range. So again, we're talking about estimation here. Let's revisit this scatter plot from section 9.1, where we were looking at what happens on days where the temperatures are hotter than some other days, and looking at what you saw from the graph was that in general, days that are warmer have more people going to the beach. Surprise, right? So we want to look at where would a line be that would fall in a place between most points, so that no points except for the outliers would be very far away. In fact, we're probably looking somewhere in here. When you do draw the line, you ideally want to have it where it's going to have some points where it intersects a real easy coordinates to work with. So I drew the line here because I've got a point right there that, if you look at that, the x is 92 and the y is 525. And then I've got another point down here where the x is roughly 84 and the x is 84 and the y is roughly 150. And even though you can see that there are more points on this side of the line than there are on this side of the line, still, if you compare how far away various points are, there really aren't any points that are dramatically farther away on either side. And that's what we really want to look for in a good line of fit. So we're going to use these coordinates to calculate the slope. And remember, slope is always rise over run. So the slope is going to be the y-coordinate of one point minus the y-coordinate of the other point divided by the x-coordinate of one point divided by the x-coordinate of the other point. And again, remember that as you set it up, you have to be consistent. So whichever point you start with, you have to be consistent in terms of your x and your y. They have to match up like that. So when we do the subtraction on this, you'll see that the change in the y values is going to be 375, and the change in the x values is only going to be 8. And then we're going to simplify that down a bit. Unfortunately, there's no number we can divide both of these by, since the numerator isn't divisible by 2 or 4 or 8, obviously. So we're just going to have to leave it like that. In terms of for estimation purposes, we can look at it that this is going to be roughly, we'll say it's roughly 47. But in an answer, you would really want to leave it like that. Sometimes these are written as decimals, so it would be 46 point a lot as you do this. So that's going to be the slope. That means that the equation of the line of best fit is going to be y equals 47x plus b. Because remember, we don't know what that y-intercept is yet, and that's what we're going to figure out next. So to figure out what the b is, we take one of the ordered pairs, and I always like to use the smaller one, the one with smaller numbers, just because they're easier to work with. And so I'm going to replace that y with a 150. I'm going to then keep the equal sign and the 47, and instead of the x, I'm going to use the 84. And now that way I can figure out what will that y-intercept be. When I do the math, I'm going to find out that that 150 is actually equal to 3,948 plus b. So when you solve for b, you're obviously going to get a negative number. And it turns out that we're going to end up with b equaling negative 3,798. If you look at the graph, that's going to be a surprise, because if you extend this line, it just goes here. But the reason why this graph is deceptive is because of this part right here. that little sawtooth, means that they actually left out lots of numbers. And if you look at the graph, you can see that they're counting not by 4s but by 2s, because there is a line in between each of those numbers. So each of these intervals up here on the graph is going to represent just 2. And so since they're going from 0 to 80, they've actually left out a lot of this graph, which they did because all the information is within this area, and that's all we're concerned about. But if you did draw an entire graph where you inserted those extra, those extra 19, 20 spaces there, this line would have plenty of time to go down all the way to negative 3,798. So for here, the line of best fit is going to be y equals 47x minus, because that's negative, 3,798. Now realistically, we're not going to have negative data in here because you can't say that, oh, yesterday negative 2,000 people went to the beach. You can say 2,000 negative people if they're pessimists, but you can't have a negative number of people. So what we would do on a situation like this is we would actually restrict it. And we would say that this equation is only good, we're only going to use it for temperatures that are really above 80 or maybe 82. And after that, the data would not be reliable. That this doesn't really help us much in terms of figuring out how many people go to the beach when it's 70 degrees out or 65 degrees out. So we would restrict the domain on it. We also would restrict it on the high end because we're not going to be interested in a number of, well, how many people would go to the beach if the temperature were 200? Because the answer obviously would be 0. Now this graph you saw in section 9.1 talking about how test scores related to the number of classes that a student missed for any reason, this is going to be harder to work with because this area, there's no graph paper here. So it's going to be much harder, in fact virtually impossible, to get accurate coordinates of any of these points. We can just sort of get a sense of things. But I put this in just to give you a sense of, here's a graph where we're going to have, increasing by 10 intervals here and increasing by 20. There's no sawtooth here, so we're not going to have to deal with that issue. But on this, we're going to expect a negative slope. The y-intercept may actually end up being 100, but again, that would be unrealistic because you certainly can't guarantee that, if a student misses no classes, they're going to get a perfect score on the test. But I wanted you to see this is sort of what a line of best fit would look like. Now, if you look at this, you'll see that no matter which side they're on, the points are roughly within the same range, and remember we use that word roughly, except for this one right here. That one's a lot farther away, but remember that one is the outlier, so that is not really, just like it didn't affect whether we called it positive or negative or no correlation or nonlinear correlation, it doesn't affect the line of fit either. We're just really looking at how does the line, where can we put the line so that way most of the points are roughly within the same range away, the same distance away from that line. Looking at that graph we had, the scatter plot we had from last time, investigating as if we look at students, do taller students end up getting better grades? And the answer was no, that really there is no correlation between how tall a student is and what kind of grade point average you'd expect them to have. So in this situation, there actually is a line of best fit. There's always a line of best fit, but it's going to be basically horizontal, which means the slope is going to be basically 0. You can see here, and this is a graph a scatter plot I got online. You can see that they're drawing it slightly going negative, so it would have a negative slope, but a very, very, very small negative slope. And the reason they did that was because they do have some points down here. Again, I would certainly call that one an outlier. This one not so much, because there are a couple, these two up rather, because you've got those points there, and you also have this point here. Then these are roughly about as far away as these are. So again, no correlation. We'll still have a line of best fit, but it's basically going to be either slope of 0, or it's going to have a slope that's slightly positive, slightly negative. It will have a y-intercept though. In this case, it's a 3.0 or 3.05. So now go back to Edmodo, do the first problem set, ask any questions that you have. You'll be using everything from this as you do the next part, which deals with linear regression.